disasters happen. Disasters happen a lot. Every year, all around the world, humanity faces both natural and man-made disasters. Wildfires in California, tsunamis across the Pacific, bomb threats in dozens of major cities, and our local Floridian favorite, the hurricanes. All these disasters result in mass evacuations, and often these evacuations result in traffic, heavy, standstill, I wish I stayed at home in the hurricane traffic. These pictures are from the Hurricane Irma in 2017, and while I joked about the traffic, it is actually very serious. With interstates backed up and cars running out of gas next to empty pumps, it took people more than 20 hours to travel from Miami to the Florida-Georgia border. A trip like that normally takes only 10 hours. In response to these issues, we studied and defined a new evacuation routing problem, the conflict-free evacuation route planning. Given a transportation network, a set of capacity constraints on roads, and the location of evacuees, our problem produces evacuation routes that can minimize the evacuation time and the movement conflict between evacuees on these routes. This problem is important to many societal applications such as emergency management planning, resource assignment, and even large event planning. For example, by analyzing the output, we can identify potential bottlenecks and critical areas in the transportation network, and we can improve the network infrastructure. In addition, we can make sure that there are plenty of resources such as gas, food, and water in the area that will need it most. Previously, we have proven that this problem is NP hard. This means it is computationally challenging and no solution exists in polynomial time. For this reason, existing solutions are either not scalable, produce wildly complex and congested road plans, or even fail to evacuate everyone in a reasonable time. We have designed and implemented algorithms that make use of intelligent data structures to decrease computational time and produce evacuation routes that minimize congestion. Our final goal is to adapt these algorithms to allow horizontal scaling by identifying spatial temporal partitions that can be individually analyzed. This would allow for the algorithms to be used for massive real-world scenarios by making use of parallelization. In times of disasters, there is a lot of uncertainty, but one thing is clear: we can do better.